Our next example from part 3 of section 7.4 states, 2 light bulbs are selected from a lot of 24. 24, we're going to pick 2 of them. We know that which 4 are defective. So amongst this 24, 4 are defective, which does mean that the other 20 are not defective. Just putting information down to deal with. Okay, what is the probability that both of the light bulbs are defective? So we want the probability that both of the ones we pick, that's really bad luck, are defective. So both defective. Let's figure out the size of the sample space first. So, because we don't care in what order we pick them, we'll use a combination. We've got 24 that we're going to pick from, and we're picking 2 of them. But we need both of the ones we pick to be from the defective side of the world. So we know that when we go to pick our 2, they have to be out of this 4 that are defective. So that would be the combination of 4, choose 2. Now, what's implied here, but you do not need, is you could multiply this by the combination of 20, choose 2, 20, choose 0, because you're picking none of those. We talked about this a few minutes ago, that the 4 and the 20 would add to the 24, and the 2 and the 0 would add to the 2. So again, this is equal to 1, so you don't need it, but notice that it is there if you want to use that as a quick check. So the combination of 4, choose 2 comes out to be 6. 24, choose 2 is 276. And if you divide that out, you get 0.0217. Okay, what about the probability that at least 1 is defective? So the probability of at least 1 defective. So what this implies is that you're picking 1 defective or 2 defective. Well, we already know the 2 defective because we just found it. So let's backtrack and find the probability of 1 defective. Let's do that first. So 1 defective means that of the 4 that are defective, we want to pick 1 of those. The other 1 is going to come from the 20 that are good. So picking 1 defective, picking 1 not defective, all over the combination of 24, choose 2. And to that, we're going to add the 6 over 76 that was both defective from before. So this is 4 times 20. Plus the 6. So that would be 80. 6 over 276. And that comes out to be 0.688, no, sorry, 0.312 if we add them together. Now, I could have done this as the probability of no defectives and subtracted from 1. So recognize we could have come in and done 1 minus the probability of no defectives. Either way works, but because we'd already figured out both defectives, I chose to go this route. This way would also work. So if we wanted to do this, we could do 1 minus the combination of picking both of them from the 20 that are good over the combination of 24, choose 2. That would also work. You'll get the same answer. So, okay, our next problem or example. States, says, example 6, an exam consists of 10 true false questions. So we have 10 true false questions on our exam. If a student guesses at every answer, what's the probability that he or she will answer exactly 6 correct? So we want 6 correct. So the probability that they get 6 correct. Okay, well, let's go look at the denominator. Again, that's where I start. So we know that, we've got 10 questions. 5, 6, 7, 8, 9, 10. And that because they're true false, there's like 2 answers here, 2 answers here, and so forth. So the denominator is going to be 2 to the 10th power. So that's 1024. What about the numerator? Well, what they're really asking me is the number of ways I can rearrange the true or the correct, the correct answers. So this one's correct, this one's not, this one's correct, this one's not. How can I rearrange the 6 correct answers amongst those 10 positions? So that would be the combination of 10, choose 6. So rearranging 6 correct answers amongst the 10 answers overall. By default, the others are incorrect, so we don't need to account for those. That comes out to be 210. 2 to the 10th power is 1,024. So 210 over 124 gives me 0.205. So if you just randomly guess, you'll get a 20% chance, 21% chance of getting all the answers correct. So not very good. Don't go guessing. I guess there's a moral to that story. And our last example is probably one of the ones that you tend to see in almost every textbook on probability. It says, what's the probability that at least 2 of the 9 justices of the U.S. Supreme Court have the same birthday? So what's the probability that in a room of so many people, 2 have the same birthday? So what we're going to do is 2 of 9 with same birthday. I'm going to do this as a complement because it's just easier. So we're going to do 1 minus the probability that nobody has the same birthday. So no birthday the same. Because I think it's an easier way to tackle it. So let's first of all figure out, well, how many birthdays are there amongst 9 people? So we know that there are 365 days in a year. So we're going to do 365 to the 9th power. So in other words, that's 9 choice blanks on what we could have as birthdays. First person could have a birthday on 1 of 365 days. The second person could have a birthday on 1 of 365 days, and so forth. So that gives us all 9 of them, right? Okay, well, we want them to have no birthday the same. So none of their birthdays are the same. So we're going to come in and do, and again, I didn't squeeze it in, but there's a 1 minus. 1 minus. So the first person in the room has 365 choices for their birthday. But the next person in the room is not going to have the same birthday. So we're going to multiply that by 364, and then we'll multiply that by 363 for the third person. 362, 361, it's not going to fit. So there's 1, 2, 3, 4, 5 people times 359. So times 359 times 358. How many people got to get? 1, 2, 3, 4, 5, 6, 7 times 357 times 356. If I multiply that all together, that's where we're at in terms of birthdays that are not the same.
Sorry, I need to plug in the laptop.
Low battery. Okay, so we have 1 minus, and it looks like I don't have any of those this multiplied out. So 0.90390537 is what this comes out to be. And 1 minus that gives me 0.09462. What is this saying? Well, this is saying if you have 9 people in a room, whether they're Supreme Court justices or not, if you have 9 people in the room, there's a 9% chance that 2 or more will have the same birthday. Very interesting. So, and it does say at least 2 of the 9, right? So that's 2 or more of them having the same birthday. And that's how we use our counting techniques in probability.